Welcome back to the Deep Dive, everyone. Today we're going to be diving into something uh, pretty wild, I think. Consciousness physics.
Oh, yeah.
Yeah, we're going to be exploring that intersection of physics and consciousness. Specifically, we're going to be diving into some of the ideas of physicist Sir Roger Penrose.
I think what is so captivating about this area is that it really pushes us to the limits of what we know about the universe and ourselves.
Yeah, it really is. It's like we're trying to solve the ultimate puzzle, right?
Yeah.
How does our subjective experience of the world, like our thoughts, our feelings, arise from the physical stuff of our brains?
Exactly. And Penrose argues that to truly understand consciousness, we need to go beyond our current understanding of physics.
Mm.
He even suggests that new physics might be needed to bridge the gap between the material world and the realm of subjective experience.
Okay, so where do we even begin with something this complex? I know you sent me some material, and it mentioned starting with something familiar, the Pythagorean theorem. Now, I remember that from high school. A plus B will C Fitzroy. Um, but how does that relate to consciousness?
It might seem like a leap, but bear with me. The Pythagorean theorem is a fundamental truth in Euclidean geometry, the kind of geometry we usually use to describe the world around us. But what if our universe isn't strictly Euclidean? What if there are hidden dimensions and strange curvatures we don't normally perceive?
Oh, okay.
Right.
Now you've got my attention. Now I'm picturing those mind-bending drawings by M.C. Escher,
Right.
where staircases seem to go nowhere and water flows uphill.
Yeah, that's a great visual analogy. Escher's work often depicts non-Euclidean geometry, specifically hyperbolic geometry. So imagine a world where parallel lines eventually meet, or where the angles of a triangle add up to more than 180 degrees. That's the strange world of hyperbolic space.
So are you saying that our brains, which evolved in a world that seems, mostly Euclidean, might be missing some crucial information about the universe, and that could be hindering our understanding of consciousness?
Yeah, that's one of the possibilities that Penrose explores. Our perception of space and time might be limited by our Euclidean perspective. What is consciousness, with its non-local qualities and seemingly impossible connections, operates on a different geometric level, one that we haven't fully grasped yet?
Okay, that's a pretty wild thought. But I'm starting to see how even something as simple as the Pythagorean theorem can open up these mind-blowing possibilities.
And this leads us to another fascinating area, the world of numbers. We're all familiar with real numbers, but even those are abstract concepts, and they have limitations in representing the physical world, let alone something as complex as consciousness.
I'll admit, math isn't exactly my strong suit,
Mine either.
but I'm willing to give it a shot, especially if it helps us understand how our minds work.
Well, you might be surprised to learn that even something like complex numbers, those numbers with I representing the square root of -1, play a crucial role in describing the universe. They were initially considered just mathematical curiosities, but now we know they're essential for understanding quantum mechanics and the behavior of particles at the subatomic level.
So something that seemed purely theoretical turned out to be fundamental to describing reality. That's kind of mind-blowing. And it makes me wonder what other imaginary concepts might turn out to be key to unlocking the mysteries of consciousness.
That's a great question, and it's one that Penrose explores as he delves deeper into the world of mathematics and its unexpected connections to the physical world. For instance, he talks about the Mandelbrot set, this incredibly intricate and beautiful fractal generated by a surprisingly simple formula involving those complex numbers that we were just discussing.
Fractals, those infinitely self-similar patterns always fascinate me. But how do they tie into consciousness?
The Mandelbrot set is a beautiful illustration of how simple mathematical rules can give rise to extraordinary complexity. And that might offer a clue about consciousness. Maybe consciousness itself arises from fundamental physical laws. Laws that we haven't yet uncovered, but that have the potential to create something as rich and intricate as our inner world.
I'm starting to see how all these seemingly disparate pieces, geometry, numbers, even fractals, might fit together in this grand puzzle of consciousness.
Exactly. And to explore these connections further, we need to dive into some of the powerful mathematical tools that physicists use to describe the universe. Things like Fourier decomposition, which helps us break down complex phenomena into simpler components, and even stranger concepts like hyperfunctions, which push the boundaries of what we traditionally consider functions.
I'm ready to dive in, even if it means getting a little lost in the mathematical weeds. It feels like we're on the verge of something truly groundbreaking, unraveling the secrets of the universe and our place within it.
It's fascinating how our exploration of consciousness has taken us on this journey through the world of mathematics. And just when you think it can't get any more abstract, we stumble upon something called manifolds.
Manifolds. Okay, that sounds intimidating. Can you break that down for me?
Imagine a curved surface, like the surface of a sphere. Now zoom in really close on a tiny patch of that surface. If you zoom in enough, that little patch starts to look flat, like a piece of paper, right?
Yeah, I can see that. It's like how the Earth seems flat to us, even though we know it's a sphere.
Exactly. That's the basic idea behind a manifold. It's a space that might be curved overall, but locally at each point it resembles flat Euclidean space. And this idea, as abstract as it sounds, is crucial to Einstein's theory of general relativity, which describes gravity as the curvature of spacetime.
Whoa, so our entire universe could be thought of as a manifold. I'm starting to get a sense of just how deep this rabbit hole goes.
And to understand how things work on these curved spaces, we need to introduce the concept of vector fields. Think of them as little arrows attached to each point on a manifold. These arrows can represent things like the direction and strength of gravity or other forces.
So it's like having a map that shows us how things will move on this curved space-time landscape.
Precisely. It's a way to visualize how forces act on objects within this warped and wonderful universe of ours. And remember those complex numbers we talked about earlier? They actually play a crucial role in describing these vector fields.
It never ceases to amaze me how these seemingly abstract mathematical concepts turn out to be essential for understanding the universe's structure. It's making me see math in a whole new light.
And this journey through the mathematical landscape leads us to another fascinating concept, Lie groups. Think of them as sets of transformations that leave something unchanged, like rotating a square. You can rotate it by 90 degrees, 180 degrees, or 270 degrees, and it still looks the same, right?
Right, because of its symmetry.
Exactly. Those rotations form a Lie group. And these symmetry groups are incredibly important in physics, particularly in the standard model of particle physics. They help us classify and understand fundamental particles and the forces that govern them.
So symmetry isn't just about aesthetics. It's woven into the fabric of the universe at the most fundamental level. That's beautiful and mind-boggling at the same time.
Now let's take this idea of symmetry and push it a step further with the concept of fiber bundles. Imagine attaching additional spaces called fibers to each point of a base space. Think of it like a hairy ball. The surface of the ball is the base space, and each hair sticking out is a fiber.
Okay, I'm picturing it. But how do hairy balls relate to physics and consciousness?
Fiber bundles might sound strange, but they provide a powerful framework for understanding gauge theories, which are essential for describing fundamental forces like electromagnetism and the strong and weak nuclear forces that govern the interactions of particles.
So we're talking about forces that operate at the subatomic level, the very building blocks of matter. Could these forces somehow be influencing consciousness as well?
That's a question that some physicists are exploring. The idea is that maybe consciousness arises from some kind of interplay between these fundamental forces and the structure of our brains.
It's incredible to think that these concepts from the realm of theoretical physics could hold clues to the mysteries of the mind.
And just when you think we've reached the peak of abstractness, physics throws another curveball Dirac's equation. This equation, developed by physicist Paul Dirac, predicted the existence of antimatter.
Antimatter. The stuff that annihilates matter when they come into contact. That sounds like something out of science fiction.
It might sound like science fiction, but it's a very real phenomenon. And Dirac's equation, which combines quantum mechanics and special relativity, was a game changer. It led to the development of quantum field theory, which describes particles as excitations of underlying fields that permeate all of space.
So empty space isn't really empty at all. It's a sea of potential particles constantly popping in and out of existence.
That's the strange and beautiful reality revealed by quantum field theory. And this leads us to one of the biggest mysteries in modern physics, the quantum measurement problem. In quantum mechanics, the state of a system is described by a wave function which evolves deterministically. But when we try to measure a system, the wave function seems to collapse, leading to a single definite outcome. And this collapse process is probabilistic and not well understood within the framework of quantum mechanics itself.
So there's this weird disconnect between how the universe seems to operate at the microscopic level and how we experience it at the macroscopic level. Does this gap have something to do with consciousness?
That's where Penrose's ideas come back into play. He suggests that gravity, which is usually ignored in quantum mechanics, might actually play a crucial role in this collapse process, the so-called reduction of the wave function. And he argues that this connection between gravity and quantum mechanics might be the key to understanding how consciousness arises.
Okay, now we're coming full circle back to the big question of how our subjective experience of the world emerges from the physical processes in our brains. So how does Penrose propose to bridge this gap between the quantum world and the world of our everyday experience? So we've explored all these incredible concepts, from geometry and complex numbers to this strange world of quantum mechanics. But how does Penrose actually connect all of this to consciousness?
Well, Penrose, along with anesthesiologist Stuart Hameroff, developed a theory called orchestrated objective reduction, or ORC, or R for short. It suggests that quantum processes influenced by gravity are happening inside tiny structures called microtubules within brain cells.
Microtubules, those are part of the cytoskeleton, right? I remember learning about them in biology class, but I never imagined they had anything to do with consciousness.
Yeah, they were thought to be just structural elements giving cells their shape. But Penrose and Hameroff proposed that microtubules could be the perfect place for quantum computations to occur, shielded from the noisy environment of the rest of the cell. And these quantum computations, they believe, could be the basis of consciousness.
So you're saying that inside these tiny tubes, there's a whole quantum world buzzing with activity, and somehow that's giving rise to our thoughts, our feelings, our sense of self. It's almost too incredible to believe.
It is a bold theory, and it has its share of critics. Many physicists and neuroscientists are skeptical about whether quantum processes can really play a significant role in the brain, especially given the warm, wet, and seemingly chaotic environment of biological systems.
So how does Penrose address those criticisms? It does seem like the delicate world of quantum mechanics wouldn't survive for very long in such a messy environment.
That's the objective reduction part of the theory. Penrose proposes that gravity plays a key role in causing the wave function to collapse, and this collapse happens spontaneously within these microtubules, regardless of whether an external observer makes a measurement.
So gravity's acting as a sort of internal observer, collapsing the wave function and creating definite states within the microtubules. And somehow these states are orchestrated to produce consciousness.
Exactly. The orchestrated part of OR refers to the idea that these quantum events in microtubules aren't random, but are somehow organized and orchestrated to produce coherent conscious experience. How exactly this happens, well, that's still a big mystery.
It sounds like we're just starting to scratch the surface of this incredible field of consciousness physics. Where do you think this research will lead us in the future?
It's hard to say for sure, but I think we're on the cusp of some major breakthroughs. We're developing new tools to probe the brain at the quantum level, and we're beginning to understand the complex interplay between quantum mechanics, gravity, and biology. I wouldn't be surprised if in the coming decades we uncover entirely new physics that helps us to finally crack the code of consciousness.
It's thrilling to think that the answers to some of the biggest questions about the universe and ourselves might lie in this strange and wonderful world of quantum consciousness. I, for one, am eager to see where this deep dive takes us next. Thanks for joining me on this journey.
The pleasure was all mine. And remember, the next time you look up at the stars or ponder the mysteries of your own mind, keep in mind the incredible possibilities that lie at the intersection of physics and consciousness. Who knows what wonders await us in the quantum realm?